This is our galaxy, the Milky Way in all its glory. Or at least, it might be. Because like every other image that shows the whole of the Milky Way, this is actually a computer graphic that is based on our best guesswork.
So what does the Milky Way really look like? We're about to find out.
In December 2013, the European Space Agency launched Gaia, a scientific instrument that will transform our understanding of the Milky Way.
It's the most advanced astronomical camera ever made and contains the biggest array of sensors ever to leave the Earth. The camera is packed with 1 billion pixels, over 60 times more than the Hubble Space Telescope cameras, and it will allow Gaia to learn more about our galaxy than ever before.
We've come to the company that built this incredible sensor to explore the story behind it. Also, what does our galaxy actually look like?
At the moment, we think that we've got a 4-spiral arm structure. A few years back, we thought we only had 3. It's amazing how the picture changes.
And physicist Jim Al-Khalili finds out how the mission will let us trace the hidden matter that shapes our galaxy.
Without dark matter, the universe as we see it simply wouldn't exist.
Plus Pete, showing us how to see the Milky Way for ourselves.
Seen from Earth, the Milky Way is a glorious sight as it stretches across the night sky. But we only get a very narrow perspective on our galaxy. And in fact, we know surprisingly little about it.
We estimate the Milky Way contains at least 100 billion stars. But so far, we've only been able to catalogue a tiny fraction, around 200 million.
We believe that it's a spiral galaxy, but its exact structure remains an open question. As does what lies in the mysterious region around its centre.
But Gaia is hoping to change all this.
Gaia is a wide-field telescope designed to scan the entire sky. Instead of staring intently at individual objects, it's designed to give us a broad perspective. It's armed with 2 telescopes that focus light onto a sensor bristling with 1 billion photosensitive pixels.
What we have here is a duplicate of one of the imaging sensors that makes up the Gaia array. In the full array, we actually have 106 of these, and so it's pretty impressive. Each one of these detectors is quite similar to the sort of thing you'll find in a consumer digital camera, but with one difference. The pixels in this are much, much bigger. The engineers have worked out that with bigger pixels, we can gather a lot more light.
So much so that this sensor is capable of capturing more than 90% of the light that lands upon it, whereas my camera at home would be lucky to get 20%.
Gaia is expected to detect and measure hundreds of stars every second. And it will revisit the same patches of sky 70 times, which will allow it to do something extraordinary.
Not only will we have the most accurate map of our little corner of the galaxy, but also, for the first time, we'll record how the stars are moving. And that is a really powerful tool.
It will allow us to predict what the galaxy will look like in the future and how it evolved. It should also help solve a puzzle. What is the exact shape of our galaxy? The problem is, how do you work it out from the inside? To find out why this is such an important question, Chris is speaking to Nicholas Walton.
This is a representation of what our galaxy looks like top down. We can see the spiral arm structures, we can see a bar structure, and here we see directly that in fact, looking at it from this direction, looking down on it, we wouldn't know if that was a flat bar, we wouldn't know if it was a bulge, because we haven't got the idea of the 3D volume.
And so this is our best guess as to what the galaxy might look like. The sun would be, I think, here, something like that. But interesting things happen near the centre.
Yes, towards the centre you can see that the spirals of our galaxy come together. At the moment we think that we've got a 4-spiral arm structure. A few years back we thought we only had 3. It's
changing all the time.
It's amazing how the picture changes based on new information and new observations and so forth. If you go in, you'll see that the star densities actually increase, and you see what looks like a bulge. It might be seen as a bulge, but now we believe that this is a bar.
And this sort of straight structure at the centre.
This straight structure across here, and you'll notice that the spiral arms actually start at the edge, at the ends of the bars, the north and the south bar. Now in the centre, the idea is that actually some of the stars are forming because of material forming and flowing down the bar into there.
So this material has perhaps flown along the bar. And actually there were some recent results that make it more complicated again.
Yes, indeed. So we've had some recent very exciting survey data looking for very bright stars towards the centre, and now we find that there's evidence of cross structure. So there's 2 bars. So all of a sudden it's even more complicated, and it's a real challenge to understand how we put this together. But this is an evolving picture. We thought we knew what our galaxy was like. Well, actually, because we're inside this very complicated structure, it's very difficult. So when we look ahead a few years to the results from Gaia, it will give us a definitive picture of what's happening.
And so what does it mean if our galaxy has these complicated structures at the centre and Gaia reveals them to us? What will that tell us about the formation of the galaxy?
Well, did our galaxy form because it was the merger of 2 massive galaxies, for instance, or was it the merger of a massive galaxy where we actually then went on and accumulated and accreted lots of little, gobbled up almost, lots of little smaller galaxies? These are the answers that Gaia will enable us to get.
And if we can get them for our galaxy, we can understand other galaxies.
We can understand other galaxies, we can understand what the universe looked like further back towards the Big Bang, all the way through to our present day universe, and get a good understanding of how galaxies were built, how they were formed, and how stars were formed within those galaxies, and that links all the way through to how planets formed.
The main focus of Gaia's work will be to catalogue millions of stars, but scientists are hoping that it will do much more, that it will shed some light on one of the most mysterious and hard to imagine constituents of our galaxy, dark matter. Dark matter is thought to be everywhere, in the depths of space, all around us. Billions of particles passing through your body every second, and yet it is also completely invisible. Physicist Jim Al-Khalili is investigating what dark matter really is, and how Gaia might help us find out more about it.
For almost a century, scientists have been searching for dark matter without success. But we know something is there.
The key is gravity. Look up at the night sky and you expect gravity to explain the distribution and movement of all the stars. But the mass of the visible universe only provides 15% of the gravitational pull needed to explain everything we see. There's no visible evidence of the missing stuff that provides the other 85% of the required gravity.
Dark matter is simply the name that scientists have given to whatever it is that's creating the rest of that gravitational pull.
Without dark matter, the universe as we see it simply wouldn't exist.
But if dark matter makes up such a large part of our galaxy, why haven't we been able to find it yet?
To begin to get your head around just why searching for dark matter is such a challenge, you first have to understand what it isn't. You might think it would be easy for me to show you dark matter, but it's much more difficult than that.
Nothing in this wood, no matter how dark, is as dark matter. That's because all normal matter reacts to light. Shine a torch and some of that light will be reflected back.
But dark matter is different. It's a substance that doesn't respond to light in any way. It neither emits light nor reflects it. But even that is only the beginning of just how profoundly different dark matter is. You see, dark matter isn't matter in the conventional sense at all, in that it's not made up of the same stuff as normal matter. Most of the evidence for the existence of dark matter is therefore indirect.
And this is where the difficulty lies. The problem is, we just don't know what dark matter is. And that's why it's so hard to study.
Scientists are trying lots of different ways to detect and understand dark matter. For example, there are experiments buried deep underground trying to capture the particles of dark matter using specially designed detectors. There are particle accelerators, like the Large Hadron Collider, which are trying to create the particles of dark matter. But Gaia will be trying a different method. It'll allow us to look up at our galaxy and deduce the properties of dark matter from what we can actually see.
It'll measure in extreme detail the effect dark matter has on the visible matter in our own galaxy. Cosmologist Dr. Andrew Ponson simulates what this might look like.
Now, of course, we think about dark matter being out there today, but you're interested in the role it played very early on in the formation of the universe.
That's right, and we think dark matter had a crucial role in making the universe like it is today. So a lot of what I do uses computers to try and work out or model what dark matter would have done throughout the history of the universe. So I can actually show you here a simulation of the way that dark matter behaves. Because it's in a computer, we can paint the dark matter any colour we like. We can make it visible. So I'm going to paint it green and show you what happens over the first 1.5 billion years or so. So I can hit go. Then we've just seen the Big Bang. The whole universe, or at least this chunk of the universe we're looking at, is expanding. And as it does so, you're seeing what happens to the dark matter over the first 1.5 billion years or so. It started out quite evenly spread out, coming towards us, but over time it forms into clumps.
So, of course, this is the dark matter which we wouldn't be able to see. How does that relate to the visible universe?
Yeah, we can switch views and show what the computer thinks the visible universe would look like at this time. Every dot of light you see here is a forming mini galaxy. It's got maybe a few million stars in it. But the key thing is that they wouldn't be there unless that the dark matter that we were seeing just before is there in the first place. It's that extra gravitational pull that all that dark matter is providing that pulls the gas in and allows it to sit there and start forming stars and start forming the universe we know today.
This is the important point. They're clumping together not because of their own gravity, although that must be important, but because of the gravity of the dark matter, which is much more dominant.
Yeah, there's so much more dark matter than normal matter that's what we think the key role of dark matter is, to pull all this stuff together and actually clump it into something that can form these stars.
How does that evolve? What does it look like today?
Well, we can use these computer models to work out precisely that. If I switch to another view, here we've zoomed in on one of those single points of light that you saw. And this is going to turn into something like our Milky Way galaxy today. So if I restart time, then what you see happening is all these different little mini galaxies start merging together. And once again, we think dark matter is playing a key role in this. It's the gravitational pull associated with the dark matter that actually pulls all these different bits and pieces together and starts assembling the present-day Milky Way, which just grows and grows.
Andrew's simulation can also predict where the dark matter that surrounds our galaxy is today.
This is the final picture that comes out of the computer model we've been watching. And what you've got here is the galaxy as we know it is some tiny little bit in the center, which of course we can't see because we're only looking at the dark matter here. And then you see that all these other blobs of dark matter around. Now, a few of these will have some stars in as well, but most of them are just too small. So we think that our Milky Way galaxy, first of all, is shrouded in dark matter, but also has all these extra blobs of dark matter around it, which are essentially failed galaxies in their own right.
Now, of course, this is a simulation. How do you test that this idea is correct?
That's where something like Gaia comes into the picture, because If we switch to where we think the stars are in our computer model, it looks something like this. The main galaxy is still in the center there, and as those small bits of dark matter fall into our own Milky Way, the stars are stripped out, and they're left in these big streams that you can see here.
So if we could see these streams of stars falling into the center, that is evidence that there's dark matter spread out to large, vast distances.
Exactly, and that's just what we're hoping Gaia will let us confirm.
So, Gaia may well give us our best evidence for dark matter and how it behaves.
But I'll give you one last thought. It might be that after we've had time to analyse the massive amount of information provided by Gaia over the next 5 years, we discover something completely different. It might be that all our calculations were in fact wrong and that dark matter doesn't exist at all. Now, in my view, this isn't very likely, but it's what makes astronomy so exciting.
The key to the success of Gaia are the imaging sensors that make up the spacecraft's billion-pixel camera. Producing these sensors requires some very delicate engineering. We're back here at the E2V laboratories, and what you can see in front of us is where they assemble the detectors. Now, it's in a clean room because of contamination such as dust. This can play two roles. If it sits on top of the detector, it stops the light or the photons getting in. But if it's embedded in the electronics, it kills the detector dead. Now, contamination is such an issue that I'm not allowed in, but we've cleaned up our cameraman, Nick, and he's showing us the close-up detail. The battle with dust is extreme. In this clean room, there is 35,000 times fewer dust particles than in normal air. They've got over 300 people making sensors for all sorts of space missions. As well as Gaia, this company has built sensors for the Rosetta Comet landing mission, Planet Hunter Kepler, and the Mars Curiosity rover. What they're actually doing in there is cleaning the detectors before they're sent off for testing. Dust isn't the only challenge in making the sensors. They also have to be designed to cope with the violent experience of being launched into space. Chief Engineer David Morris simulates the conditions of a launch with a vibration test. So what sort of force are you putting it under?
It goes up to about 50 times the force due to gravity on Earth, simply by this vibration in 3 axes.
So it seems really odd, because you spend so much time making these wonderful detectors, and then you put them through hell.
They have to go through hell, because otherwise we won't be confident they'll survive when they go through the hell of launch. But it is always traumatic, worrying about whether or not what we've designed and built will survive this sort of extreme violence.
This process reveals the key to successful space engineering: extreme precision married with extreme robustness.
Next, how can you view the Milky Way for yourself? Pete's here with a few tips and a guide to touring the galaxy.
It's a great time of year to spot the Milky Way.
Unlike in the spring and the autumn, the plane of the Milky Way rides very high in the sky during the winter and the summer, and each view gives us a completely different perspective of our own galaxy.
In the summer, we look through the Milky Way towards the galactic centre. This bright summer Milky Way snakes across the sky, revealing a dense path of stars, punctuated by dark dust clouds.
In the winter, we get a much more subtle view of the Milky Way rather than the bright view we get during the summer months. And this is because during the winter, we're looking out through a thinner portion of the Milky Way to the universe beyond.
The result is remarkably different, with a faint band stretching up from the horizon. However, it is no less beautiful and is packed with some stunning deep sky objects.
At this time of year, the best place to see the Milky Way is within what's known as the Winter Triangle, and this is made up from 3 bright stars.
The winter triangle is formed by drawing an imaginary line between the stars Betelgeuse in Orion, Sirius in Canis Major, and Procyon in Canis Minor.
The winter triangle is a very clear pattern, and if you have a dark sky, you can often see the Milky Way running right the way through the centre of it. But if you do have trouble making out that subtle, faint light from our own galaxy, then it's worth scanning the region with a pair of binoculars, because there are some fantastic clusters to be seen there.
A few favourites are NGC 2244 in the centre of the Rosette Nebula, and M41, located just below the bright star Sirius.
Of course, the Milky Way isn't the only thing on offer this month. Jupiter's really well positioned, and it's about to offer up a really rare event. So with details of this and other highlights visible in this month's night sky, here's my star guide.
The open cluster M41 is located just to the south of the winter triangle below Sirius and should be easy to find with binoculars. Southeast of the triangle, two further clusters, M46 and M47, can be seen. The main constellation in this direction is faint Monoceros, the unicorn. Within the mythical beast's triangular head sits NGC 2244, the open cluster at the heart of the wonderful Rosette Nebula. As the Milky Way heads north, it passes a distinctive curve of faint stars in Gemini. It is here you'll find M35 and the dimmer NGC 2158. Finally, look out for brilliant Jupiter, which dominates the view high to the south around midnight. On the 24th of January, between 0628 and 0653, three dark moon shadows of Io, Europa and Callisto will be visible on the planet's disk at the same time. This doesn't occur very often, so make sure you get outside and have a look.
Now, back to Gaia, and it'll be a few years before we get the first new star catalogues and maps from the data that it's sent back to Earth. But it's already giving us exciting science about unusual phenomena that we might call transient signals. Every now and then, our telescopes record flashes in the night sky, many of which are the results of stars exploding in what we call supernovae. These are rare events, but they have enormous scientific value. In these stellar deaths, we can reveal how many of our elements were created, and also how the universe is expanding. What Gaia will do is will help us find many more of these things as they happen, and it might even help us discover a new type of exploding star. Maggie is talking to Dr. Simon Hodgkin, who'll be releasing information about these signals as they're found.
Simon, can you describe to me, what is a transient signal?
A transient signal is one that doesn't last for a terribly long time. So it's only there for a small amount of time, and it's important to react quickly to learn what it is before the light disappears. So there's a whole range of events, transient events. There can be super flares on stars like our sun, which can last for hours to days, but there can be supernova events that last for weeks to months.
So if you find a supernova, what can it tell us?
So supernovae are a mystery. We've known about them for a long time. We know there are lots of different kinds of supernovae, but the physics of what kind of star gives rise to which kind of supernovae is a little bit, I would have to say, flaky. So we're trying to find as many nearby supernovae as possible to try and understand where they came from and what kind of supernovae there are.
And they've already made a number of discoveries, one of which caught the scientists totally by surprise.
We found something really rather rare and really rather exciting.
They were alerted after Gaia recorded an explosion on a star in our galaxy.
We took an image. This was taken in a telescope in Italy. So we decided to take a sequence of very short duration images. So this is the first 20 or so images look like this, and this is another one at random, which looks pretty much the same. And it's this star here. And that's our star that blew up. And Essentially, it's still there, it looks good. The very next image, 30 seconds later, the star actually vanished. It's got 1,000 times fainter, I think, essentially. So suddenly we've gone from a star that's pretty bright to a star that's not there. We carried on looking at it. Every 30 seconds we took a new exposure, and over the next minute, it started to reappear and then got back to its previous level.
So what's going on there?
So our interpretation is that we have two degenerate white dwarf stars orbiting each other. And in fact, these disappearances happen periodically.
Oh, as one goes in front of the other?
So one goes in front of the other. Every 50 minutes, one star is occulted by the other. It's called an eclipse.
Yes, but that doesn't make sense to me, because if you've got two bright stars, you have lots of brightness, half the brightness, then lots of brightness again. So why does it disappear?
That's right. So both objects need to be the same size, but one is essentially bright and the other is very dark. And so when the dark star passes in front of the bright star, it blocks it out. But when the dark star goes behind the bright star, you don't really see any change in the brightness level.
Yes.
And because they're so perfectly aligned, we can do something you can't do with these kind of stars normally. It's very rare. We're very lucky to have found the explosion with Gaia and done this follow-up. We can measure their masses, we can measure how heavy they are, and we can measure their radii. And if they're what we think they are, and these two stars will merge together as they lose energy through gravitational radiation, they could form a Type 1a supernova.
Type 1a supernovae are a unique form of exploding star that are important for astronomy. Cosmologists can use them to measure the size of the universe. But exactly how they form is a mystery.
So the question is this a progenitor of a 1a? And I hope in my lifetime we'll be able to make the measurement that will tell us whether or not these are growing together and could explode, or they're growing apart. And this is not the 1a progenitor we're looking for.
But I suppose if you see them coming together, then the hope is that they will go supernova.
That's exactly right, but it may take millions of years.
It's a fantastic discovery. And one of the great things about this mission is that you could help find others like it. Because Gaia data isn't just for scientists.
So the idea is every time we find something dramatic, a transient event happening in the sky, we publish it to our website. So we write down the coordinates and the brightness of the object. And all those data are public, and anyone can go and look at them. And if they have access to a telescope, they can go and follow up our objects. And I would love it if they could tell us what they are, share their data, and help us classify the kind of things we're finding, which are potentially very rare, very exciting.
Because I guess Gaia is going to be inundating you with lots of these. And we want the amateur community to join in and help resolve the problems.
That's absolutely right. I can't keep up. We're finding 3 or 4 or 5 a day. We don't have the resources to follow them all up, whereas the amateur community can help for the ones that are bright enough for them. And even in schools, there are access to a network of telescopes that the school children can have access to and trigger follow-up observations of objects we've found.
So school kids get involved and do real science.
That would be fantastic. I would love that to start happening.
Exciting times ahead.
It's a busy, exciting time ahead.
Yes. Thank you so much.
Thank you.
To find out more about Simon's project, you can visit our website at bbc.co.uk/Sky at Night. It really is a fabulous chance for schools to get involved in pushing back the frontiers of knowledge.
That's it for this programme. Next month, we'll be scanning the skies for UFOs to reveal how the search for little green men has transformed our knowledge of the universe. In the meantime, get outside and get looking up.
Good night.
And The Sky at Night BBC book is available now. We're heading north from Peru here on BBC4 this evening as Jago Cooper discovers how the Inca Empire met its demise. The final part of Masters of the Clouds is at 9. Next though, clang, clang, clang goes the trolley as Time Shift celebrates the golden age of the streetcar in just a moment.